start a brand new type of differentiation today. Brand new type of derivative. And this one is called implicit differentiation. Now I'll kind of explain what that means before we start here. Okay. So looking at our derivatives so far, we've only been taking derivatives of functions that we say are defined explicitly. And some examples of that are here. So explicitly defined functions are functions where we have y on one side and then all the x's on the other. So for example, here we have y on one side and it's equal to all these things involving x. Same here, same here. Everything involving x is on one side, everything involving y is on the other side, and there's only just one y value, okay? Now, I'll show you some examples of functions that are defined implicitly, okay? And here we just have a mix. So on the left-hand side, we have a bunch of things involving x and y. They're all kind of mixed together. Okay, now we've actually seen implicitly defined functions in maybe another class before. Does anyone know what this function is? What is
a squared plus b squared equals c squared?
Good. There's actually a different, that is true. If I graph this function, what would it look like?
A circle.
A circle, right? This is a circle of radius 5, right? So if I were to graph this function, it would look like this. And even though I'm calling it a function, this really isn't a function because it doesn't pass the vertical line test, right? Okay. Now, it's a function, okay? And I'll explain why it's called a function, even though it doesn't look like one, okay? I can turn this into an explicitly defined function, the function on the left, by solving for y, right? So I could subtract x squared on both sides to get y squared equals 25 minus x squared. And I could take the square root of both sides. What am I forgetting when I take the square root? Plus or minus sign, right? Okay, so this function, if I turn it into an explicitly defined function with y on one side, everything else on the other, is actually two functions combined together. Okay, so I have y equals the square root of 25 minus x squared. And then I have y equals negative the square root of 25 minus x squared. Okay. And actually what this is the top half of the circle on top and the bottom half of the circle on the bottom. Okay. So normally when we have implicitly defined functions, it really is just a bunch of different functions like stuck together to make one big function. Okay. Okay. A lot of the times though, you can't just take an implicitly defined function and turn it into an explicitly defined function. An example of which is this one, right? X cubed plus y cubed equals 6xy. Now you can try this on your own if you would like, but getting y on one side isn't going to work here. It's going to be very difficult to get y by itself here because we have a y cubed and a y on the right side. Okay, so the reason why we don't make everything explicit or having y on one side is because sometimes it's just not possible or it would take a while to get y by itself. So we're gonna have to figure out how to find the derivative of these guys when we can't really solve for y, okay? So to help with this, we have implicit differentiation, which is a whole new sort of subsection of finding derivatives. It involves the chain rule, and it looks a little bit different than what we've been dealing with before, okay? I know this is really abstract. Let's go through these steps and then do an example, and I think that will clear things up. Okay, so first of all, you're going to start with an equation that has both x's and y's in it. Might have different situations going on, but we will start with this. 2, we're going to assume that y is an implicit function of x, which means y is like what we want to find the derivative of, and x is like our independent variable. Okay. Oh, I'm going to give you a sheet for my. The third step is we're going to differentiate differentiate both sides of the equation with respect to x. Okay, and this is going to involve the chain rule, and I'll show you how. Okay, and then finally, we're going to get dy dx. So that's what we want to find. Now, that might not make any sense because it's very abstract. Let's do a few small examples of how the chain rule would be required. Okay, so for example, on the side, if I were to find the derivative with respect to x of, let's do x squared. Okay, that's easy. It's just 2x, right? Now, here's where it gets different. If I want to find the derivative with respect to y of y squared, it would be 2y. Okay, so the thing on the bottom is what we're taking the derivative of with respect to. Okay, now it gets a little bit trickier. The derivative with respect to x of y squared is different because I'm finding the derivative with respect to something that isn't the variable in the derivative. Okay, this is where the chain rule comes about. Okay, what's my inside function here? What is the function on the inside?
Y squared.
Not y squared, but not 2. That's actually on the outside. Y, right? Y is on the inside of this function. If y was, for example, 3x plus 2, 3x2 would be on the inside, the square would be on the outside. Does that make sense? Yeah. Now the outside would be something squared. Okay, so if I were to find the derivative of this, it would be 2 times the box to the first power, right? And then I would multiply by the derivative of the inside. What is the derivative of the inside, Michael?
Y prime.
Y prime. I'm going to write it in the Leibniz notation, but y prime is also dy over dx. Okay, so putting this all together, the derivative of 2y is going to be 2. So the derivative of y squared, sorry, I'm looking up, is 2y dy dx. Okay, so essentially, when we find the derivative of something involving y, it's going to be that derivative with respect to y times dy dx. Okay, so we're just multiplying anything with y by dy dx. Okay, let's see if we can do this in our heads a little bit more. What do you think the derivative of 3y to the 5th is going to be?
15y to the 4th times dy over dx.
Perfect. So we're literally finding the derivative with respect to y and then multiplying it by dy dx. Okay. What about the derivative of sine y? Yep, cosine y, dy dx, or y prime. Okay, so just find the derivative with respect to y and multiply it by dy dx. That's all I mean when we're finding the derivative when we have y's, but we're finding the derivative with respect to x. Okay. All right, let's move on. Let's get a little bit more complicated, okay? Let's say we want to find the derivative of our circle, okay? We want to find dy dx, and I don't want to solve for y, I just want to find it implicitly, okay? So let me actually get my notes out to make sure I'm not writing anything wrong here, okay? Of course, I can solve for y and find the derivative with respect to x, but it gets a little tricky because we have two functions kind of being hidden here, okay? Okay, so the way we're going to do this is we're going to find the derivative on the left and the derivative on the right, okay? So I'm going to find the derivative with respect to x of the whole left-hand side. And that's going to be equal to the derivative on the right. Okay, so the derivative on the left has to be the derivative on the right, okay? I know you can kind of imagine this in your head, but whenever we have a derivative of addition, we can always break this up into the derivative of each value. Now, of course, you don't have to write this, but it kind of helps me out. So this is the derivative of x squared, the derivative of y squared, and the derivative of 25. Okay. Okay. Easy question. What's the derivative of x squared?
2x.
2x. What's the derivative of y squared with respect to x?
Y. Y prime.
Yeah, 2y prime or 2y dy dx. Okay. And what's the derivative of 25? 0. Good. The derivative of a number is just 0. Okay. So we've done this. We figured out what our derivative is on both sides. Now, this doesn't really help us because we want to find the derivative of our function, dy dx. Okay. Well, that's right here. Maybe we should solve for that function itself. Okay. So if I want to get dy dx by itself, what should I do on both sides first, Michael?
Subtract 2x.
Yeah, subtract 2x. So I'm going to get 2y dy over dx equals negative 2x. Okay. And then finally, to get dy dx on one side, what should I do on both sides?
Divide.
Good. Divide by 2y. So I'm left with dy dx equals negative 2x over 2y. Okay. And of course, since there's a 2 on the top and on the bottom, this is negative x over y. Okay. This is actually my final answer because it's kind of hard to get y by itself. In this example, I can solve for y and plug it in so I only have x's. For simplicity's sake, let's just leave it like this. This is my final answer. Okay. So basically, at any point of my graph, I know how much is changing if I just plug in x and y into my derivative. Okay. Any questions so far? I'm going to do a little bit more of a complicated example. If we flip our page, we'll get x cubed plus y cubed equals 6xy. Okay. Now, the fun thing about these sort of graphs with explicitly defined functions, since they have the weirdest looking graphs, a lot of them have names because they're kind of more useful in real life. This one is called the folium of Descartes, which is interesting and cool to say. Let's find the derivative of this one. Okay. So I want to find the derivative of the left and the right. So the derivative of x cubed plus y cubed equals the derivative of 6xy. Okay. Let's do the left side. I think that's a little bit easier. What's the derivative of x cubed? 3x squared. What's the derivative of y cubed? 3y squared times dy dx or y prime. Okay, so that's just using the chain rule here. Let's talk about the right-hand side. Okay, now I have 6x times y. What do you think is really going on here? The product rule, right? We have something with x multiplied with something with y. This is actually two things being multiplied together. Looks like we're going to have to use the product rule. Okay, now it doesn't matter which one we call f or g. I'm going to call the first one f, the second one g. And just as a reminder, I'm going to write up the product rule. Fg prime, what does that equal using the product rule? Okay, good, but with your, I like Evelsander's whole formula here. What was the second part? GF prime, good. Getting 2 steps ahead of me here. That's good though. Okay, so using the product rule, the derivative of f by itself is 6x, right? So that's f. What's the derivative of g? Y prime or dy dx? Okay, so that's g prime. And we have to add g, which is y. So that's g. What's the derivative of f? 6, good, and that's f prime. Okay, so I just used the product rule to split this up into a bunch of things being added together here. I'm just gonna clean this up here. We got 3x squared plus 3y squared dy over dx. We've got 6x dy dx and 6y. Okay, so we just kind of cleaned everything up. A little bit tricky here, right? We have dy dx over here, and we have dy dx on the other side of the equation. How can I get dy dx by itself? Like, what would I do, Sam?
You would subtract either, it doesn't matter, but you can subtract either 6x dy dx or 3y dy dx to the other side and then factor out dy dx.
Okay, good. So I think what Sam's saying is maybe we should get everything with dy dx on one side and get everything else on the other side so we can factor it out. Okay. And if you don't see where I'm going here, let me do it and kind of see what it looks like. Okay. So, I'm going to do Sam's suggestion of subtracting the 6x dy dx on both sides. And if we do that, then I guess we have to subtract 3x squared on both sides, so that all the dy dx's go on one side and everything else goes on the other. Okay, so it looks like we'll be left with 3y squared dy dx minus 6x dy dx equals 6y minus 3x squared. Okay. So all I did was make sure that all the dy dx's were on one side and everything else was on the other side. All right, then I think Sam said, once we're here, we can factor out a dy dx, right? Both of these terms have a dy dx on it. So that means, what's left over if I factor out the dy dx? Perfect, 3y squared minus 6x. And this is 6y minus 3x squared. Okay. Finally, to get dy dx by itself, looks like the opposite of multiplication is division, right? So we can divide by 3y squared minus 6x on both sides. And we get that dy dx is equal to 6y minus 3x squared over 3y squared minus 6x. Okay. This would be fine for me on a test or quiz. WebAssign might not like this answer. Does anyone, can anyone see why?
You can do that answer.
It does, okay. Then I'll just leave it like that. You can take out a 3 on the top and the bottom. And let me just show you what that would look like. You could factor out a 3 on the top to make it 2y minus x squared, and factor out a 3 on the bottom to be y squared minus 2. And the 3's would cancel out and get 2y minus x squared over y squared minus 2. I wouldn't expect you to do that on a test or quiz though, because what I boxed is an accurate derivative. All right.
Where's the x go?
Oh, did I forget it next?
I think the x just material.
In what step? The
one.
Oh, you're right. You're right. Thank you. All right. That looks a little better, doesn't it? All right. Any questions so far, other than my mistakes during class? All right. Let's flip our page over. I want to do one more example, and then I'll leave you on your own, I promise. Let's find this derivative here. We have the sine of x plus y times y squared times cosine x. Okay, so I want to find the derivative of the left. And I want to find the derivative of the right, right? Okay, let's just talk about strategy here. Looking on the right, what strategy do you think I'm going to use for y squared cosine x? Product rule, just like we did last class, right? Or not last class, on the last example. So that's definitely product rule because we have two things being multiplied together. What do you think we're going to do on the left? Chain rule, right? It looks like we have an inside x plus y, and we have an outside, which is sine. So it looks like this one's going to use the chain rule. Okay. Okay. I know some of us can do chain rule in our heads. I like to go through the whole inside outside thing so we can kind of see how it all pieces together. Okay. Looking at the left, what's the inside function? Good. And what's the outside function? Sine. Good. So we have x plus y inside sine. Okay. Now, when I find this derivative, I'm going to take the derivative of the outside first. What's the derivative of sine? Cosine of whatever's on the inside, right? And I'm going to multiply that by the derivative of the inside. What is the derivative of x plus y? Good. 1 plus dy dx. Okay. Everyone good with the derivative on the left? Okay, I have to put the inside this box, right? X plus y. But it looks like the derivative on the left is all good. Okay. Derivative on the right, we have to do the product rule. Of course, it doesn't matter which one is f and which one is g. I'm going to make y squared f, and I'm going to make g cosine x. Okay. Now, just a reminder that product rule is fg prime equals fg prime plus gf prime, right? Okay. We have f, which is y squared. What's g prime? Negative sign, good. Okay, so I just did f and g prime. What is, oh, I know that g is y prime. Oh no, g is cosine x, sorry. What is f prime? 2y dy dx, right? So we just take the derivative with respect to y and tack on a dy dx, and we're all good. So I just did g times f prime. Okay. So I'm just going to clean everything up on this next line. This becomes the cosine of x plus y, 1 plus dy dx. And because there's a lot of parentheses here, I'm actually going to put the cosine in brackets just to kind of section it off from the 1 plus dy dx. On the right, we have negative y squared sine x, and we've got a 2y cosine x dy dx. Okay. Here's where things get a little bit trickier, right? It looks like we can still try to get the dy dx's on one side and everything else on the other side, but the dy dx is actually like embedded in parentheses now, okay? Michael?
You can distribute it.
Good, right? If the dy dx is embedded in parentheses, that's an example of something that we have to, I know, it's a lot of writing. This is like a thing that we have to expand out, right? I can't just get dy dx on one side if I don't distribute first. So our next step would be to distribute the cosine to the 1 and the dy dx. Looks like this is going to give us a cosine of x plus y times 1, which is just cosine x plus y. And then we've got a cosine x plus y times dy dx. Okay. On the left, looks like we have the same thing. I'm sorry to make you write this a billion times. Now it looks like we can get the dy dx's on one side, everything else on the other side, right? Okay. So the way I'm gonna do that is subtract off the 2y cosine x dy dx on both sides. I'm going to add on the subtract off the cosine x plus y. And it doesn't matter if you decided to do it the other way. I'm just going to do it this way because that was the first thing I thought of. And let me change colors here. Okay. On the left, it looks like we have cosine x plus y dy dx minus 2y cosine x dy dx. On the right-hand side, we have a y squared sine x minus cosine x plus y. Okay. What's our next step? Factor out the dy dx, right? That's what we're looking for. So dy over dx being factored out. What goes on the inside of my parentheses here?
Cosine x plus y minus 2y cosine x.
Perfect. Cosine x plus y minus 2y cosine x. The right side stays the same. And I know if you want to just skip some steps while I'm writing, that's also fine. Give your hand a break. And finally, we can divide both sides. Oh.
You just didn't write it down.
Oh, I'm sorry. Thanks. That helps a lot. Wow, I'm making some student mistakes this time. No, I make mistakes all the time. Student mistakes are teacher mistakes. Okay, finally, we can divide both sides by that factor, and we're going to be left with negative y squared sine x minus cosine x plus y over cosine x plus y minus 2y cosine x. Whew, that was a lot of writing, wasn't it? All right. Anyone have any questions about example 3? I think I saw David first, or Zach first.
I'll say technically couldn't cosine x plus y cancel out.
No, it actually wouldn't, because the denominator has, it's like combined with something. If the cosine x plus y was by itself, you could break this into 2 fractions and cross them out. But we can't actually cross these out. A good example is if you did, I don't know, 1 plus 4 over 4 plus 5, you couldn't just cross out the 4s, right?
Yeah.
Yeah.
Multiply that.
Yeah, if we have multiplied like 1 times 4 over 4 times 5, then you can cross them out, but not with addition. All right, Dave, what was your question?
2 things. 1, will this be posted?
Yes.
Yay. 2, how do you write so fast?
I don't know.
How am I supposed to keep up?
I'm sorry. I think the iPad's like easier for me to write on. Like it goes really, like it glides really fast. Normally I don't write this fast, but I'll post the notes so you can copy this down a little bit faster. Sorry about that. Sometimes I get carried on with class too, and I don't remember to slow down. But okay, how about this? Example 4 and example 5 are both questions that I think we can do at this point. Why don't we start with example 4? If you have more time, go on to example 5. And to kind of make this go a little bit easier, I'm going to give you the answer to example 5 just in case we don't get to it. The answer to 5 is cosine x minus cosine x plus y over cosine x plus y minus cosine y. Okay. Now, let me give you some time to work on example 4 and 5. Definitely work together if you're feeling a little funky about this, if this is new to you, but we'll come back in a little bit. I'll bring you this to you. Look at the back.
That's exercise.
Start with 4. If you have more time, try 5 examples. In this situation, very similar to what we've been doing in the last example. On the left-hand side, it looks like we have a y times a function, right? Whenever we have multiplication, what rule are we going to use? Product rule, right? So on the left-hand side, you probably should use the product rule. And on the right side, we have addition, and there's really no rules surrounding that. So we're actually just going to take the derivative of the right-hand side. Okay. Sam, did you write up example 4?
Yes.
All right. Do you kind of want to take us through your steps here?
Well, first, usually I just rewrite the problems when it's like longer and I can't really do it in my head.
Mhm.
So for like, I don't know. And then I just use the product rule, got dy over dx times cosine of x. And then I just simplified y times negative sine x into negative y times sine x. So that would make it easier to put onto the other side.
Mm.
And then that equals 2x plus 2y dy over dx.
Oh,
And then I switched both, I added y sine x to the other side and then subtracted 2y dy over dx so that the dy over dx's are both on the same side.
mhm.
And then factor dy over dx and then divided the parentheses.
Perfect. Very nice. I like how you showed all your steps. We got here. One thing I want to say about this, if you got, for example, I think I saw someone get this answer, negative 2x minus y sine x. Oh, is it cosine? Oh, I think it might be sine, right? And then I think on the bottom you got like someone got 2y minus cosine x. This would also be correct. You just did the steps in a different way. If you factor out a -1 from the top and on the bottom, you would get the answer in purple. Okay, so don't freak out if the signs look a little bit different than like the answer on the answer sheet or my notes here. You just did the steps in a different way. The answer is still right. Okay. Any questions on example 4? All right, moving on to example number 5. This one, let's just talk about strategy before we go through the answer. On the left-hand side, we have sine of x plus y. What rule do you think we're going to use there? Chain rule, right? Because we have an inside and an outside. So this is an example of the chain rule. And on the right-hand side, it looks like there's nothing being multiplied or something on the inside and something on the outside. So we're just going to take the derivative normally on the right. Okay. Michael, do you want to take us through your answer here?
Sure. Derivative of sine
Mhm.
x plus y would be cosine x plus y times the derivative of the inside, which is 1 plus y prime over 2y dx.
Mhm.
And then on the other side, you have sine x plus sine y, and the derivative of sine x is cosine x, and the derivative of sine y is cosine y dy dx.
Mhm.
And then you distribute on the left the 1 and the dy dx.
Mhm.
So it would be cosine x plus y plus cosine x plus y dx.
Mhm.
And then on the other side, it's the same. And then I got all the dy dx is on the same side. So I had dy dx cosine x plus y minus the dy dx cosine y. And I moved the other one to the other side.
Mhm.
Cosine x minus cosine x plus y. And then you take out the dy dx's, and you get dy dx times cosine x plus y minus cosine y. And then keep that same, and then you divide by cosine x plus y minus cosine y to isolate the dy dx. And then
Perfect job. Any questions on example 5? I think as we continue on with these, if you do more practice with implicit differentiation, you'll see that like the steps are basically the same for any of the problems. The hardest part is kind of just to get started and figure out what your strategy is. But the steps kind of end up being the same no matter what the question is. So if we don't have any more questions on this, then I guess I'll let you out like 4 minutes early.